Hello and welcome to Business Analytics. We are in the third module called Prescriptive Analytics, and in my opinion, this is the most difficult module. And we are going to strongly base this on this book, Spreadsheet Modeling and Decision Analysis by Cliff Ragsdale. And of course, you don't have to buy this book. Everything you need should be in these lectures and PowerPoint slides, but I am going to heavily borrow from this book. So you'll notice the difference between other slides where I start with the Introduction to Business Analytics, and here I'm talking about linear programming. And that is because prescriptive analytics is more than linear programming, and there is a lot more complex mathematical and algorithmic operations. But for this class, we're going to focus on linear programming. I hope you understand that. So we're going to be very specifically look at one technique in prescriptive analytics, because this could take an entire year. There's a lot more involved, and therefore we're just going to focus on this one technique. For those of you who still don't know who I am, this is Hari Rajagopalan, and I will continue this module, and hopefully you'll enjoy it. So we have finished descriptive analytics and predictive analytics. And in these two, I believe I've successfully avoided trying to use math. And I have tried to take the math away and describe everything in English. Now, unfortunately, in prescriptive analytics, which is where we are, I cannot do that. You are going to see a heavy amount of math. And so this lecture here is an introduction and a small practice problem for you to start looking at how to do this, how to translate English to math, and then from math to Excel. So let's talk a little bit about what prescriptive analytics is. So we all face decisions about how to use limited resources such as time, money, workers, machine capacity. So these are all resources which have a certain specific level, and we don't have more than a certain amount. And we want to make the best decisions for our company, for ourselves. And a lot of times we have objectives like we want to maximize profit or minimize cost. So mathematical programming, of which linear programming is part of, is used to find the optimal or most efficient way of using limited resources to achieve the objectives of a business. And it's also called optimization. So what are the applications of optimization? You can apply optimization to marketing, finance, human resources, any area in business, also in military, and almost anything else in the world. You can always model things in math and then optimize it. And the characteristics of an optimization model or a mathematical model is that you have decisions you need to make, and you have to figure out when you read a problem what kind of decisions you have to make. You have constraints, and then you have objectives. So the general form of an optimization problem is usually a maximum or minimization of a function, and a function which contains a bunch of independent variables, x1, x2, x3, and then it's subject to a certain set of constraints. So these are b1 to bk to bm are all constants. And if this is a linear, we talked about linear optimization. If the functions are linear, the problem is called linear programming. And linear means these variables x1 and x2 don't have a square or a cube. They aren't multiplied by each other. They're only added or subtracted. And when you only add and subtract the unknown variables, that becomes a linear program. So linear programming looks something like this, where C is a constant, this is an unknown variable, and you're going to add or subtract these, and it's subject to certain constraints. Here again, A11, A12, A1n, all of these, and B are all constant numbers. And you're either adding or subtracting, and they're less than, greater than, or equal to some value. Okay, so again, if all functions in the optimization are linear, it's called linear programming problem. Even if one is not linear, then it becomes nonlinear, and that creates a whole bunch of new problems. So when you have linear problems which are linear, you can guarantee that the solution you have is actually optimal. So let's take an example. Let's look at Blue Ridge hot tubs. This is a problem. And here we have, they sell two types of hot tubs, Aquaspa and Hydroluxes. And Jones, the manager, needs to decide how many of each type of hot tub to produce in the next production cycle. So he buys pre-fabricated fiberglass hot tub shells and adds a pump and tubing to create his hot tubs. The supplier can deliver as many hot tub shells as how he needs, and therefore this is not a problem. The same type of pump is used for both hot tubs. He has only 200 pumps available, so he can't use more than 200 pumps. And the difference from manufacturing is Aquaspa requires 9 hours of labor and 12 feet of tubing, whereas Hydrolux requires 6 hours of labor and 16 feet of tubing. And he has about 1,566 production labor hours and 2,880 feet of tubing. So each one has only, needs one pump, right? And here are the production labor hours and feet of tubing. And he earns a profit of $350 for each Aquaspa he sells and $300 profit for each Hydrolux he sells. And he is confident he can sell all the hot tubs he produces. So the question then is, how many Aquaspas and Hydroluxes should he produce if he wants to get the maximum profit, right? And so let's rethink this model. The first thing you got to do with all these problems is take a pen and paper and start removing all the words and just putting the numbers down, right? So let's look at this problem. So you have Aquaspas, which require one pump, 9 hours of labor, 12 feet of tubing, and it's $350 in profit, right? You have Hydroluxes, second product, which needs one pump, 6 hours of labor, 16 feet of tubing, and has $300 profit. And what is available? We have 200 pumps, right? So 200 pumps, we have 1,566 hours of labor, and 2,880 feet of tubing. So this kind of makes it a little bit more clearer on what we need and what is available, right? So put it in a table. Let's go ahead and dump it all in a table, and this is something you should do with a paper and pen. Kind of go ahead and put it into a table, right? And when you put it in the table, it makes things pretty easy to read. And so here now you have pumps, you have labor hours, tubing, and unit profit. And this, putting it in this form, makes it easy for you to do your mathematical equation. So the 5 steps in linear programming is, first read the problem, understand the problem, right? And then you want to identify the decision variables. So in this case, we can identify the decision variables as, and let me get a pen here. So we are looking at decision variables as, and I would then first start off with Aquaspa, right? You have number of Aquaspas and number of Hydroluxes you need. So you have Aquaspas and number of Hydroluxes you should produce, right? This is basically what you need to decide in this problem. So once you know this, things get easier, right? And you can now, let's go ahead and put that in. Let's call it X1 and X2. Now this is how the book does it, X1 and X2. I would advise all of you, if you're going to do this problem, to use A and H. Try to use the labels, decision variables, as labels you can easily identify and recognize. If you're strong in math, you can use x1 and x2, but I think for this class, I would suggest all of you use A and H. A is the number of aqueous spas to produce. H is the number of hydroluxes to produce. Then you're going to state the objective function as a linear combination of decision variables. So what is the objective? So next thing you got to think about is, what do you want to do? You want to maximize your profit. So it's $350 for aqueous spas and $300 for hydroluxes. Therefore, the total profit would be 350 multiplied by x1 plus 300 multiplied by x2. Why? If x1 is 1, that's 350. If x1 is 2, then it's 700. If x1 is 10, that's 3,500. So it is 350 multiplied by the number of aqueous spas you produce, plus 300 multiplied by the number of hydroluxes. Now we are going to state the constraints. So let's look at each constraint, right? So here are 3 sets of constraints, and let's look at each one, and let's convert them into English. So the first one we are looking at here, right here, right? We're saying number of pumps used should be less than 200, right? Because you don't have more than 200 pumps. And how do you know number of this here gives you number of pumps? And how does it give you number of pumps? Well, if you're going to produce X1, if you're going to produce 100 aqueous spas, you're going to use 100 pumps. If you produce 200 aqueous spas, you're going to use 200 pumps. So when you produce X1 aqueous spas, you are going to then use X1 pumps. Similarly, you're going to use X2, you're going to produce X2 hydroluxes, you're going to use X2 pumps, right? So here is number of pumps is less than 200. The next constraint we know is that total, let me get this, total labor hours used is less than 1566. So if you produce 1 aqueous spa, you use 9 hours, right? If you produce 1 aqueous spa, you use 9 hours. If you produce 10 aqueous spas, it's 9 multiplied by 10, right? So aqueous spas is 9x1, 9 multiplied by x1, because this is the number of aqueous spas. Similarly, for hydroluxes, it's 6 multiplied by x2, right? So this is the total labor hours here. Similarly, this one is total number of tubing is less than 2,880. If you produce 1 aqueous spa, 12 feet, 2 is 12 multiplied by 2, 3 is 12 multiplied by 3. So this is 12 multiplied by x1 plus 16 multiplied by x2. That's the number of hydroluxes. So that gives your constraints. You also have to put upper and lower bounds for the decision variables. And in this particular case, both these values are positive. And this is always, these are called non-negativity constraints, in the sense that all these variables here cannot be negative. They're always positive, okay? So let's look at how we are going to solve this linear programming. First, the intuitive way, then I'm going to show you a graphical way, and then finally we'll do it in Excel. So the idea is that, the first kind of default idea is each aqueous spa generates the highest profit. So let's forget about hydroluxes, just let's make aqueous spas. So how many aqueous spas would we produce if we didn't produce any hydroluxes? We essentially put x2 is equal to 0, right? And therefore then we look at all the constraints. If x2 is 0, x1 is less than 200. And then second constraint, which is your second equation, 9x1, because x2 is 0, is less than 1566. That gives us x1 is 1566 divided by 9, that's 174. And then 12x1 is 2,880, right? If those of you who are trying to figure out what I'm doing is I'm taking these values from this equation, and I'm just taking away x2. I'm putting x2 as 0 because we're only going to produce x1. right? So x2 is 0, so all these values become 0, and therefore I'm able to find different values for x1. So here x1 is less than 200, x1 is less than 174, x1 is less than 240. And therefore, if x2 is equal to 0, x1 cannot take a value more than 174 because labor hours will prevent you from doing more. The maximum value you can get is 174. Plug this into the profit function and you get a profit of 60,900. So this is what we call as a feasible solution. But is it the best solution? And the answer is probably no, right? So let's try to solve this graphically. So here we have constraints that define the feasible region, and the best point in the feasible region is the optimal solution. So for a problem with two variables, which is like what I call as a toy problem, it's easy to plot it and find the optimal solution. And we're going to do that. So let's look at this. This is x1 and x2 plotted, and I'm going to look at x1 plus x2 is equal to 200. That's the boundary, right? And what we'll do is now we'll look at if x1 is 0, if x1 is 0, right, then x2 will be 200, so this line. And then if x2 is 0, x1 is 200. And so we have this boundary line. And because we're saying it's less than, it is this area, this blue area, which is the feasible region. Anything outside on this side is not feasible. So now let's look at the second constraint. Now we're looking at 9x1 plus 16x2 is less than or equal to 1566. So first we look at equal to, and we do the same thing. Let x2 be equal to 0, then x1 will be 1566 divided by 9, which gives you that 174. And then if x1 is 0, x2 will be 1566 divided by 6. And so that should get you 261. And so now the blue region, this part and this part get cut off. And the blue region, because this is also less than, will be here exactly, right? And now let's put the third constraint. So the third constraint now looks at the tubing constraint. Again, x2, put x2 is equal to 0. x1 is 2880 divided by 12 will get you here, right? That's 180. And then x1 is 240. 2880 divided by 12 is 240. x2 is 2880 divided by 16 is 180. And you get that. And again, you're looking at the less than line. So here is the feasible region here. Again, this one is no longer feasible. Anything in the white is no longer feasible. The blue line is feasible. So now that we have these values, let's plot a curve of the objective function. So here's the feasible level. And so we're taking this 350 x1 plus 300 x2 and we plot the objective function here. And so anywhere random, we can start here at 0, 0, 0, which means the profit is 0, but you can start moving it upwards because that'll increase your profit. At this point here, you can plug in these two values. x2 is 116.67 and x1 is 100, and you get 35,000. But you can move it even up further. You can move it up further, and here we're seeing that it's about 52,500, right? Using 150, producing 150 aquaspas and 175 hydroluxes. But you can even, there is more blue region, and so you can move it further right up to this point. This is the highest point you can move it. So it looks like this ends up being your maximum value, right? Your X increases, your Y increases, but anything beyond this in this angle of this line will be outside. So this is your maximum point, right? So that's your optimal solution. And so you can calculate this optimal solution by looking at this line here and then this line, and when they cross, that's your optimal solution. Now, you don't have to do this. Excel will do it for you, okay? So optimal solutions occurs where pumps and labor constraints intersect. So here we're looking at x1 plus x2 is 200, 9x1 plus 6x2 is 1566, and then you can go ahead and you have two unknowns and two equations. And when you solve it, here x2 is at 200 minus x1. And now here 200 minus x1, you plug it in here for x2, right? And that reduces x1 to 122. And then x2 becomes 78. So at 122 aqua spas and 78 hydroluxes, you get a total profit of 66,100, and that's your maximum value. So here is the technique. We start with objective value 0. You can look at all the extreme values. So here at 0, 180, it's 54,000. At 80, 120, that's another extreme value. It's 64,000. At 122, 78, it's 66,100. And at 174, here are the extreme values. At 69,000, obviously, then this is your maximum value. And there is no other value which is higher than that. So summary of the graphical solution, and like I said, you don't have to do a graphical solution. This is just to show you what's happening when Excel does it. Once we get to 3 or 4 variables, you cannot do a graphical solutions because you can't put a 3-dimensional or 4-dimensional problem in the chart. Second, you plot the boundary line, you identify the feasible region, locate the optimal solution by plotting the curves or enumerating the extreme points. Okay. So here are the special conditions or anomalies to LP models. You could have alternate optimal solutions. You could have redundant constraints. We'll talk about what each one is. You can have unbounded solutions. You can have infeasibility. So here's an example of alternate optimal solution. So here, if you look at this, if this curve, objective function curve, is 450x1 plus 300x2, all these points become alternate optimal solutions, right? It's anywhere in this curve, it's optimal, right? So you can actually get the same answer with different combinations of x1 and x2. Now, so this is actually a good thing because it gives you options of producing different amounts of aqua spas and hydroluxes. Here's an example of a redundant constraint. So here's the boundary for tubing constraint. Here is the labor constraint, and that's the feasible region. Now, if the pump constraint is something like this, right? It's about 225 here, right? So this does not cross anywhere in the feasible region. So this is what's called a redundant constraint. Everything below it is already occupied, and so this is not needed at all, right? This is called a redundant constraint. Unbounded solution happens. So let's assume here is this x1 plus x2 is equal to 400, and here is minus x1 plus 2x2 is equal to 400. And if that's the objective function, right? If something is greater than, especially this side and this side are the feasible region, this can keep going to infinity. This objective function can keep going, and there's nothing that prevents it. Nothing that bounds it. There is no ceiling here that prevents this from going this way. That's called an unbounded solution. Let's talk about infeasibility. So let's assume that the first feasible region, the first constraint says this should be less than 150. And the second one says, second one says it should be greater than 200. Now, that's not possible. It's not possible for x1 plus x2 to be less than 150 and greater than 200. That's infeasible. So then your solver will throw an error. So let's do the review. Here is the model, right? And here is the aqua spas and hydrolux. Here's the setup. Now we're going to talk about how we're going to set it up in Excel, right? And let's I'll first show you in PowerPoint, and then I'll actually do it step by step in Excel. So the first thing you have to do is to take this model, this mathematical model, and write it down. Have it in a piece of paper, or if you have a snapshot of it, you need to have this mathematical model always with you, all right? Then you're going to open up Excel, and we'll walk through this process step by step of how to do this. So then the next step is to go through Excel, and in the first row, I'll show you in Excel how to do it in the first row or the first column. But in the first row, you're going to put both these variables, x1 and x2. Then you're going to leave the second row blank. Second row is called the changing cells. Excel is going to put the values of x1 and x2. So the value of x1 will be in cell A2. The value of x2 will be in cell B2. All right. Then you're going to put the objective coefficients. So 350 and 300, these are the numbers attached to the letters. They are called coefficients, right? In this case, these are the objective. This is the objective and this is the objective coefficients. So this is 350 and 300. Okay, you're going to put that in. Then you're going to go through each one of those constraints and take their coefficients. So if you have something like x1 plus x2, the coefficient is 1, right? So you put 1 and 1. x1 is 1, x2 is 1. Then you're going to put 9 and 6, 9 and 6 here. 12 and 16, you're going to put 12 and 16 here. All right, everybody with me? Now, the next step you've got to do is to leave the C column blank. Don't touch it right now. And you're going to go ahead in the next column, go ahead and put these values. So remember, for the objective, there is no right-hand side value. And then you're going to go ahead and put 200, 1566, 280 down. All right. Now that we've got this down, we are going to fill up the C column. The first thing to do, this C here contains all the equations which you have here. So 350 is not 350 multiplied by x1 plus 300 multiplied by x2. That comes in C3. When I say equal to A2 multiplied by A3 plus B2 multiplied by B3, the equation here gives you your objective function. Similarly, when we do 1x1 plus 1x2, that's this formula here. So C4 gives you the left-hand side of this constraint. Similarly, C5, you'll notice, gives you 9x1 plus 6x2, 9x1 plus 6x2. And the last one gives you this. Now, x1 and x2 greater than 0, I'll show you how to do that. There's a default setup in the solver, and you can do that automatically. So, if you have to select each one of these cells, it's going to take you a long time. There is a separate formula in Excel called sum product. And sum product pretty much does what you're doing here. And the reason the sum product is more preferable is if you have x1 to x10, and then you have 30 constraints, you're going to do A2 multiplied by A3 plus B2 multiplied by B3 plus C2 multiplied by C3. And you'll never finish the problem. So the sum product function, right? And you see here, sum product, you're going to select A2 and A3. Sorry, A2 and B2. You're going to select this first row. And you're going to put a dollar sign here. And then you're going to select the second row without any dollar sign. And the reason you put a dollar sign is when you copy this down, A2 and B2, which is always used, will not change. But A3 and B3 change to A4, B4, A5, B5, and so on. Does that make sense? All right. So now that you've done it, you've set up the problem, right? And so here you go. You have set up the problem. This setup here is a secondary setup. So remember, I call it the horizontal method, where you have your variables in one row, and then all the formulas come in one column. Now I'm flipping it here in the what I call it the vertical setup. Here the variables are in one column. X1 and X2 are here. These are your decision variables or changing cells. Your objective function is right here. So you're going to select sum product. You're going to select this first column, and then you're going to select the second column. B2, B3, you got a dollar sign, so when you copy it, it does not change. And then you're going to put your coefficients, your objective coefficients, your constraint coefficients right here, and here the sum product, and here is the right hand side of your values, right? So, and I'm going to show you how to do both in Excel. We're going to work through step by step in Excel. So before we go to Excel, let's review what we did. It's important you understand the objective of the product, whether you want to maximize or minimize. You need to identify your decision variables. These are things you don't know. The computer needs to decide for you. You need to make a decision, and you want the computer to help you with that. You build the math models. You have the entire narrative in English, but it has to be translated into math. And then you're going to build your Excel model. Okay? So here is an example of the Excel model, and here is the setup in Solver. We're going to go through all this and solve in Solver so you don't have to do any of this. Okay, so we're going to stop here, and the next video, so this video does not contain the Excel implementation. It is the next video which will have the Excel implementation.